time and also brave the rain for coming over here, to come over here. So, as Singapore, okay. So, without much further ado, I'll let Prof. Emre over here to introduce to us the concept and the techniques behind the transcribing software that we have seen in May. So, you remember the transcribing software? No? Okay. Those who don't know will do the demo later. No, just kidding. Okay. So, without much further ado, a round of applause for Prof. Emre.
Thank you. Thanks a lot for inviting me here. I will be talking about development of code switching, automatic speech recognition systems for multilingual societies. It's also the title of my talk. And I'm currently working in Human Language Technology Lab in US. But I'm also affiliated with AI Speech Lab here in this building on the 5th floor. So it will be a rather long talk, so I thought maybe having like an outline will be good, to know where we exactly are. Before I start, I should say that I have many colleagues contributing to the content I will be presenting today. So I will acknowledge them at the end of the talk. I thank them before starting. In the beginning, I will introduce what is automatic speech recognition, code switching, more fundamentals of these two terms. And then I will go ahead with the approaches to code switching, automatic speech recognition, like how it started, how it evolved. Of course, technology changes, new models come and go every few years, let's say. Then I will move to different scenarios. First, I will start, of course, with Singapore, our case. We are living in a multilingual society, so code switching is common practice. And then we will have a demo, so I would like you to come here and try our real-time demo. So I will need some volunteers for that. And then in the second part of the talk, I will be a bit more technical, where I will be talking about low-resource code switching scenarios and building a code switching ASR system for multilingual scenarios. So it's more than 2 languages, let's say. And these languages will be from Europe and Africa, namely Netherlands and South Africa, and then I will conclude the talk. Let's start with the basics. So automatic speech recognition is actually speech-to-text problem. So you have microphone samples and you want to move to text. So as simple as that. And while doing this, we have certain resources. Like acoustic models, which contains the acoustic information of the language or the languages. Language models, which keeps the statistical information about the word sequences in the language. N-grams are the most popular ones. They are still used. And finally, a pronunciation lexicon, so that we can map from our phone models to words. While right before we output the text. So these 3 components will be crucial, and I will be referring to them in the later part of my talk. So it's good to mention them in the very beginning. And code switching is, I think you are in daily life doing this, it's not a new concept. But it's continuous alternation between 2 languages. So the most famous language pairs, I put a few of them here, like Mandarin English, Hindi English in India. People also do a lot of code switching. Ukrainian Russian, German French in Switzerland. Frisian Dutch is a smaller case, but I have studied it for 3 years, so I also put it here. Zulu English is also just an example from South Africa. So we mainly have 2 types. or 3 we can say, I will come to that. Intrasentential code switching is like you make a switch to the other language in the boundaries of a single sentence. And then intersentential is more like you say one or more sentences and then switch and in the other language say another sentence. So these are the most prominent cases, but there is also intra-word code switching, which is a very challenging case, as you can imagine. It is like conjugating a, let's say, Mandarin verb like you do in English. So then everything is mixed up, and it's a huge problem, also for automatic speech recognition systems. So what is the main challenge we are posed? It is actually our ASR system should be able to recognize both languages, and also it should be able to handle the switches between languages. So what does it imply, code switching to an ASR? So we have great ASR systems out there doing amazing job on high resource languages like English, or I don't know, let's say commercially attractive languages. I mean, it's like these generic ASR systems are doing a great job these days. But with code switching, they don't work. They just don't work because they can't work. I mean, they're not ready for the challenge I have just mentioned. So we need to adjust these basic components so that the ASR can handle code switching. So the first component was acoustic modeling model I have just mentioned. So acoustic model captures the phonetic information. So for this scenario, we should capture the phonetic information for both languages. So we have, because we have 2 languages or more languages, we have more phonemes, which means more phonetic variation. Yeah, that's more challenging, as you can imagine. For the language model is crucial because it should enable language switches. So if there is no examples of switching in the language model, the language switching will be hindered from lacking switches in the language model. And it also should be able to assign probabilities to word sequences from both languages, like mixed word sequences. So one Mandarin word, one English word, and then it should be able to assign probabilities, which means that it should have seen some examples during training. And finally, pronunciation lexicon. We should have the words and phones of both language to be able to recognize 2 or more languages. This is rather trivial, I think. So let's move to the approaches, the general outlines of these ASR systems that has been applied to code switching data so far. There are 2 main streams. On the left, you see, actually that's how it all started. So first a language identification system and then an automatic speech recognition system was the first idea to solve this problem. So what you are doing is, in the beginning, you are doing language identification, which is, yeah, I mean, you can train a language LID system, of course. And at the back end, you have 2 monolingual systems, like monolingual Mandarin and monolingual English. And the other stream of approaches is all-in-one approach. Actually, this has become the dominant way of attacking the problem recently. So what you are doing is you're just training, well, this is also a bit more neural networking. You are just building a single neural net that can accommodate the information of both languages. Let's go into a bit details. So the conventional way, let's say, of doing is the language identification and followed by an automatic speech recognition system is a good idea, but the problem is it's prone to error propagation. because LID, language identification, is still, I mean, it's not a solved problem or something. It's still a challenging task. And all the errors you make at the front end will have like serious consequences at the back end, because you may end up sending an English utterance to the Mandarin speaker. So there is no way of saving it also. And especially, I mean, this is especially a problem when the code switching happens like in a single sentences. Like, you know, the switch happens, if it happens like in over a few seconds, then that will be a problem for the LID system. So you really need a high precision language identification to successfully realize such a system. But recently, yeah, we have moved to these kind of all-in-one approaches. There are mainly two ways of performing automatic speech recognition using a single model. So the first one is language dependent models. Let's say you have a neural network, and at the target layer you have a softmax, separate softmax for each language separately. So here the nice thing is, let's say you have one high resource, one low resource language. The low resource language also benefits from the information of high resource language because of the shared hidden layers. Because while you are training your neural network, this data passes through the shared hidden layers, which implies that later your like low resource language will also benefit. And we have simple tricks to separate two languages, like adding language markers to the words or to the phones in your pronunciation lexicon. So that's how you actually realize such a system. And then language independent models are using, actually in the beginning you need some linguistic information to be able to build such a system. Because what you do is you first map all the phones from both languages to like a common phonetic alphabet, like using international phonetic alphabet or something. Then what you do is, okay, these are my phones, and then you just throw the bilingual data in the training, and you learn like a common softmax for both languages. This has been shown to help with low resource languages as well, because you know, if you have a phone, common phone, this phone will get a lot of data from the high resource language. But there is also a risk of being like if one language has overwhelmingly high amount of data compared to the other, this one will be a problem, especially for the low resource language, and it will have the tendency to act as a monolingual ASR, only recognizing the dominant language, let's say. So all the systems I will be presenting today are language dependent models. So each language has a different softmax. And a recent trend in automatic speech recognition. So if you go to a conference these days, like a speech conference, you will keep hearing about these end-to-end systems. This is like it's nice in the sense that it works like the architecture is like an encoder-decoder architecture with some attention in the middle, let's say. What is nice is you can directly move from speech features to characters. So it's like you can even go from the waveform to characters. So it's like wave to text directly. So you don't need explicit language modeling or lexicon. Yeah, I mean, this is also something interesting. Later, I will present some of our initial findings using end-to-end ASR systems as well. and then compare them to the conventional way of doing automatic speech recognition with these with all these resources. So let's talk about Singapore a bit. Well, Singapore is multilingual for sure. Well, already existing commercial ASR systems are designed for single language, most of them. I have seen in the last conference, Microsoft has now a Hindi-English system. I think it will increase, it will be more and more that companies are also offering code switching ASR solutions. But yeah, it's a bit limited now. So I would like to show you here a short video from my colleague. Let's see. We are supposed to hear something, but anyway, you were supposed to hear my colleague reading this text. So this is like a, I will just restart it. So this is like a comparison of like Google, Amazon, Siri, and our automatic transcription system. And my colleague is highly code switching while saying this. And yeah, you can just see the outputs from different systems. And I mean, it's impossible for a monolingual system to handle that kind of a text. I will just play it for the last time so that you can now you know where to focus now. So as you see, our ASR often switches between Mandarin and English, and all the other systems are just you only see English words. So they're inevitably recognition errors. I mean, it can't be otherwise. So for this reason, we just design ASR systems that support multiple languages and that can handle language switches. That's also an important aspect. Well, coming to Singapore, in languages, of course, we have 4 official languages, but many other languages are also spoken. In this talk, I will be giving my examples from Mandarin and English, but all these ideas can simply be extended to, let's say, Malay and English or any other language pairs. We are also building, actually I met a colleague in Malaysia who built recently a Malay English system. We are also busy building our Malay English system, but we have a well-established Mandarin English system, so I will be giving an explanation on how we get our systems working actually, so that it's like a simple recipe how to build a code switching ASR. So for the acoustic modeling part, of course, with the acoustic modeling, the most important thing is data. You need data where you have code switching actually. And we are very lucky in this sense with Mandarin and English. We have CME corpus, which has been collected in multiple efforts. And what we do is, in my previous demonstrations, I have just shown a fully connected feed-forward DNN, but these days acoustic models are a bit more fancy. I just put one example from Kaldi automatic speech recognition toolkit. That's by far the most popular toolkit. It's open source. I think every group who does ASR research more or less uses Kaldi these days. So what you do is you just train such models using your code switching data. And thanks to the availability of this data, this is not an issue for us. Of course, it's challenging. I will show you some numbers. There you will see how challenging this problem is. But still, it enables us to work on such systems. And then the other aspect is language modeling. So how can we obtain code switching language models that will allow code switching? So the easiest way is to train on the transcriptions of code switching speech, because there is already code switching, and finding code switching text is a big problem. It's not easy at all, because we code switch when we are speaking, but when we are writing, we don't really code switch, or it's less common, let's say. So we just use the transcriptions. Of course, the more speech data you have, the more transcriptions you have. So having more speech data helps also a bit with the language modeling. And then finally, we have like a pronunciation lexicon which contains words from both languages. As you see, we mark the phones here with SGE, which is Singaporean English, and Man is Mandarin. So that's the way we distinguish between the phones of both languages. And the words are obviously different thanks to different orthography. So I would like to present some results that my colleagues has run. And while training these systems, I should say that we are using thousands of hours of data. So we have multiple databases as well. Like CME is the one I've been talking about. It's only 95 hours. I say only. It's a good amount actually for code switching data, but compared to monolingual, it's a bit small, of course. And we have multiple English and Mandarin monolingual databases. It is common practice in ASR to increase the amount of your training data by playing it slightly slower and faster. So that has been shown to be useful. That's what we are doing too. So it's just like you triple your data in such an easy way. And of course, while training our neural networks, we are using multiple GPUs to accelerate the training. Otherwise, only with CPUs, it takes a lot of time. I will give some more implementation details. As I mentioned, for conventional ASRs, we are using the Kraldi toolkit. And for end-to-end systems, we are using ESP.NET. It's just proposed like early this year, and it follows Kaldi scheme. In that sense, if you are used to Kaldi, going to ESP.NET and building an end-to-end system is rather trivial. So we are just sticking to this toolkit, ESP.NET toolkit for end-to-end systems. Well, we train, like in Kaldi, there are very many models, acoustic models that you can try. Like the most conventional one, GMM, HMMs, that has been used still, like 10 years ago, people were still using Gaussian mixture models together with hidden Markov models. But now we have more LSTM, long short-term memory, time delay neural network models, which are way more complicated than the GMM HMMs, but you also see the difference in the results. I will also show you the huge difference. For language models, we train standard 4 grams on our 100 million word database. And this database is from the training transcriptions and also from some newspapers like Straits Times and some other newspapers that are available in Singapore. And we have a pronunciation lexicon with 360k words. We have more Mandarin words than English, but that's okay. Mandarin has 209 phones. Of course, they are tonal, which increases the number of phones compared to English. We have 42 phones for English. And the evaluation will be in word error rates. For the ones who don't know what word error rate is, it is simply the ratio between the errors, we say. There are 3 types of errors in automatic speech recognition: substitution, deletion, and insertion. So substitution is when you switch a word with another word. Deletion is when you remove a word. and insertion is when you add an extra word which is not in the ground truth transcription, divided by the number of words in the reference ground truth transcription. So this is the word error rate. So this is how we quantify the performance. So let's see some numbers. These are all CLST systems. So these are not end-to-end. These are more conventional systems. So when you take a look at the GMM, HMM, for example, the first row, it's like, well, I should also mention we have two test sets. One is Mandarin dominant, the other one is English dominant. So it's like where the most spoken language is Mandarin and English. Apparently, in this case, English dominant set is more difficult than the other one, but it could have been the other way. So what we see here is there is a huge gap between what we have been using 10 years ago and now. As you see, with a 20% word error rate on the Mandarin dominant set and like 28% of the on the Singlish test set. Here we have also some end-to-end systems. Well, I already mentioned these numbers, but these are also our best numbers. I mean, end-to-end systems cannot go beyond the conventional recognition scheme. So, well, it's still not huge. It used to be way larger. The gap between end-to-end systems used like a few years ago, it was a huge gap. But now it's like 4 or 5% absolute difference. But still, if you want to implement and like if you have concerns about your customers, you of course it's still not comparable. So therefore, we are still using like the conventional LSTM, TDNN acoustic models, which are giving the best performance. So I brought you our demo today. I just need to change the screen to our demo computer, and I would like you to come and try this. I will be the one first getting it, but I can only visualize the monolingual English part. So I can't go beyond that. Sorry. I only had 3 weeks of Mandarin so far, so my Mandarin is not that good yet. But okay. Okay, let's see. Is this okay, there we go. So let me first check if everything is all right. Okay, let's see if our recognizer is doing a reasonable job. Okay. Well, as you see, English works. Now I'm inviting some Mandarin English speakers to here to test this system. I'm also curious. Please. Anyone who wants to try?
Must be Singlish.
Yeah. Well, that's also an interesting point. I mean, now you look at the transcriptions. I'm not speaking Singlish. I'm just I'm Turkish, and I have a Turkish accent. So it's still doing pretty. I mean, it's not amazing, but it's good. I mean, it's you will understand what I'm. Yeah. Okay. What I'm saying. So English works fine. If you want to see Mandarin working, I need your help. Otherwise, I'm proceeding to the second half of the talk.
No, sorry, anyone wants to try to me? You go. Okay, I'll try.
Thanks.
Which one is that?
Well, I think you can take a look there.
Oh.
And just, I mean, you can put it on, but speaking to the microphone should be enough.
Hello, 你今天吃饱了吗？ Hello， 你今天吃饱了吗？
It's okay.
还没有吃饱。你吃什么？吃拉萨。
Also a bit English.
Yeah,
The worst thing is I have no idea if it's working or not.
It's not working very well.
Yeah, the code switching takes a bit of time because now I'm speaking English, but it's using. Okay, now it switched over.
You know what's the problem? You should have an ideal distance between your mouth and the microphone. Maybe a bit. Well, it's
Okay.
like this will be fine.
Okay.
Because clipping is not it's an issue.
Okay. Jordan, what do you do during the weekend? 去打球了吗？去打球了吗？Okay. Jordan, what do you do during the weekend? Cannot say one. Jordan, 你今天去哪里吃饭？Okay.
Yeah.
The fun is supposed to be Mandarin for rice, actually.
Yeah. Okay. So as you see, I mean, there are some still some issues,
Yeah.
but I think it's still nice to see. I mean, I brought this. I thought this would be fun. I think you liked it. Thanks for your help.
No problem.
Also, we have seen some Chinese characters out there. It's always nice
Yep.
to see them together. So yeah, okay. I will just move back to my slides and then go ahead. Better stop it because otherwise it will recognize all the. Should be okay. Thank you. Sorry, I think I need I still need your help. Yeah. It's okay. It's wrong. Okay. I don't understand the problem. Just a second. Things I can see there, but not here. Yeah. And there's no signal there.
Dual screen.
takes a while. Okay, maybe I can just wait. Just a second. I'll just try one thing, because now it should come. It's kind of weird. I mean, how did we start? Anyways, it was just working.